This video is about titration curves. By the end of this video, you should understand what information can be determined from a titration curve. You should be able to describe on the particle level what is happening at each point in a titration. You should be able to determine Ka from the half titration point of a titration. And you should be able to choose an appropriate indicator for a titration. Let's look first at strong titrations. When we say strong, we're referring to a titration of a strong acid with a strong base, as seen in the curve on the left, or a titration of a strong base with a strong acid, as seen in the curve on the right. In titration curves for strong titrations, we see a very sharp, long change in pH at the equivalence point. Due to the fact that the equivalence point scans a wide range of pH values, there are a wide variety of indicators that are appropriate for strong titrations. We'll look at indicators a little later in this video. Looking at the particle level at the strong titration curve, notice that initially all we have in solution are H+ and Cl- ions. This is the acid that we'll be titrating. This is the unknown. As we begin to add titrant, NaOH, we begin to see that we have some Na+ ions present. We'll also begin to see a decrease in H+ ions, since the OH- ions being added react with the H+ ions to form water molecules. At the equivalence point, we see that all of the H+ and OH- have reacted to form water, meaning there's no unreacted H+. At this point, all we have in solution are Cl- ions from our initial HCl and Na+ ions from our NaOH titrant. These are both spectator ions, and they're all that's present in solution at the equivalence point. If we continue to add NaOH past our equivalence point, we see a second plateau. At this point, there's no H+ left to react. Therefore, we begin to build up excess OH-. This excess OH- will cause this increase and finally plateau in pH. Looking now at weak strong titrations, these are titrations where we titrate a weak base with a strong acid or a weak acid with a strong base. Notice that in a weak strong titration, the pH change at the equivalence point is much more gradual and much shorter. This is due to the fact that in this region we're actually forming a buffer solution. Recall that buffer solutions are the result of a weak acid and its conjugate base or a weak base and its conjugate acid. Consider the fact that we started with a weak base in this case. As we add strong acid, it reacts completely with that weak base, turning any reacted weak base into its conjugate acid. Therefore, as we add strong acid, we end up with a mixture of weak base and conjugate acid, which we know is a buffer system. Therefore, we end up with a very gradual change in pH, since the buffer solution is actually resisting pH changes. Likewise, we see this here in the weak acid titration. We began with a weak acid, some of which becomes converted into its conjugate base as we add strong base to the solution. When we have a mixture of weak acid and conjugate base, we have a buffer solution, which again resists pH changes. Once the buffer capacity has been exceeded, we react all of the weak acid or weak base to reach the equivalence point. It's very important to understand that any time a strong acid or strong base is involved in a titration, the titration reaction will go to completion. Even if we start with a weak acid or start with a weak base, adding a strong acid or strong base to that solution will force the reaction in the forward direction only. It's also interesting to note that the equivalence points for a weak strong titration are not 7 as they are for a strong titration. Looking back at the titration curves from the previous slide, we see that this weak base titration has an equivalence point below 7, and our weak acid titration has an equivalence point above 7. Let's consider why this is. Again, our weak acid strong base titration results in an equivalence point greater than 7. Consider the fact that as we titrate a weak acid with a strong base, we produce the conjugate base of the initial weak acid. Consider the example shown here. Here we're titrating a weak acid, acetic acid, with a strong base. This reaction will go to completion since it's a neutralization reaction using a strong base. Therefore, all of the weak acid will be neutralized to form acetate and water. Recall, however, that weak acids have relatively strong conjugate bases. Therefore, the resulting conjugate base, the acetate ion, is able to react with water molecules to establish the equilibrium shown here. This equilibrium includes the formation of a small amount of OH-. This is what causes the pH of the equivalence point of a weak acid titration to be slightly above 7, this extra OH- resulting from the equilibrium established. Considering now a weak base with a strong acid, here we see equivalence points with a pH less than 7. Again, through the titration of the weak base, we form the conjugate acid. Consider the example here. Our weak base, ammonia, is titrated with a strong acid. This reaction goes to completion since we have a strong acid, neutralizing all of the ammonia to form NH4+. However, again, recall that weak bases have relatively strong conjugate acids. Therefore, this conjugate acid can establish an equilibrium by reacting with water to produce H3O+ ions. This increased amount of H3O+ will decrease our pH slightly, resulting in a pH at the equivalence point of less than 7. Now let's look at this from the particle level. Again, at the starting point of our titration, the only thing present is our unknown acid solution, in this case acetic acid. Note that almost all of the acetic acid is undissociated since it's a weak acid. There may be a few H+ and acetate ions floating around in solution, but in large part we just have acetic acid molecules. As we begin to add strong base, the strong base, OH-, is able to pull the H+ off of the acetic acid molecules, resulting in the formation of acetate ions and H2O. It will also leave behind a spectator sodium ion. So at this point, we have some unreacted acetic acid, some acetate from which the hydrogen has been pulled off by the OH-, and some spectator sodium ions. In addition, we have the water that's formed from the neutralization. Notice that at this point, we have a weak acid and its conjugate base. Therefore, we see this buffering action in our pH curve, this resistance and change to pH, since we've formed a buffer solution. However, since we're dealing with a strong base, we will continue to neutralize all of the acid until there is no more H+ to react with the strong base. At that point, all of the H+ have been removed from the acetic acid ions, resulting in acetate ions, spectator sodium ions, and water formed from the H+ removed from the acetate ions and the hydroxide that had been added. Again, as we saw with strong-strong titrations, when we continue to add base after the equivalence point, it will essentially just build up in solution since there's no H+ left to react. Therefore, after the equivalence point, we'll see spectator sodium ions, some hydroxide ions, and some remaining acetate ions. Notice we've simplified the case here and not considered the fact that the pH is above 7 as we did in the previous slide. We can account for that here in this box when we consider the fact that these free acetate ions are able to react to a small degree with some water molecules to form additional OH-. That's done to a very small extent, so it's not shown in the box since we're only dealing with a small number of particles. It's also possible to determine the acid dissociation constant from a titration curve. From the Henderson-Hasselbalch equation, we see that the pH will equal the pKa when this ratio is equal to 1. That occurs at something called the half neutralization point, or the half titration point. That's the point at which half of the initial acid has been converted to conjugate base through neutralization. At that point, this ratio will equal 1. This will drop out of the equation because the log of 1 is 0, and pH will be equal to pKa. Looking at this on a titration curve, we see that the equivalence point on this weak acid titration occurred at 25 milliliters. Therefore, our half titration point, or our half neutralization point, occurred at about 12.5 milliliters. At this point, half of the initial HA had been converted into A-. Therefore, our pH is equal to our pKa. So, using our titration curve, we can find the pH at the half titration point to determine the pKa of this acid. Judging from the graph, it looks to be about 4.7. Finally, let's consider acid-base indicators. An acid-base indicator is used to mark the endpoint of a titration via a color change. Phenolphthalein is one of the most common that you've definitely used in the past. So how does an indicator work? Essentially, an indicator is just a buffer system. It contains a weak acid and its conjugate base. Here I've used IN to abbreviate indicator. What makes an acid-base indicator special, however, is that the weak acid is different in color from its conjugate base. Consider what happens when we place this indicator in an acid or a base. This will cause the equilibrium position to shift. If we add it to a solution where the pH of the solution is less than the pKa of the indicator, the excess H+ will push the equilibrium position to the left, resulting in an equilibrium position that favors the acid form, turning the acid color. For phenolphthalein, this would be clear. On the other hand, if you put it in a solution with a pH greater than the pKa of the indicator, the excess OH- will consume the H3O+, causing this concentration to decrease and the equilibrium position to shift to the right. This will cause our equilibrium position to favor the conjugate base, or the base form, and turn the base color, in the case of phenolphthalein, pink. An indicator is in the middle of its color change when the concentration of the acid form of the indicator is equal to the base form of the indicator. Therefore, the color change occurs when the H3O+ concentration of the solution is equal to the indicator's Ka. We can see this here using the Henderson-Hasselbalch equation. When this ratio becomes 1, our pH is equal to the pKa of the indicator. Therefore, when choosing an indicator, you want to choose an indicator that has a pKa as close as possible to the pH of the titration solution at its endpoint. This ensures that the color change of the indicator will coincide with the endpoint of the titration. Here's a list of common indicators. Notice the color change range is equivalent to the pKa of the indicator in each case. That brings us to the end of this video. Let's review our goals. First, we looked at what information can be determined from a titration curve. Then we learned to describe on the particle level what is happening at each point in a titration. Then we looked at how to determine the Ka from a half titration point. And finally, we looked at how to choose the appropriate indicator for a titration.